So welcome guys to a new video, and I should have made this video earlier, but let's get into the video. As you can see, I have put the real life weight as per the antenna suggests. I have mimicked the overall weight distribution and going there to check the damping of the system. There you can see the sensor right there. You can see as maintained as possible, and there is a iron weight which is distant from the sensor so that no magnetic interference can be introduced in the system. There is a dummy load which would be our counterweight. So let's see what are the major problems that you are going to face when you program via this program. I will put program in every video description, and let's get into the problem. So there you can see, if you go over to the this line number 64 and line number 65, there you can see the two factors, two gains, azimuth gain and elevation gain. So those are the gain that the motor uses to rotate. The higher the value of this gain, the harder the motor will rotate. So in order to minimize the oscillation of your system, put these two values much lower, and let's start from there. If you see very slow response, let's just go over to the 1 2 value, such that you can then increment there from and test your system so that the oscillation can be minimized. And these two value, you can see alpha, azimuth alpha and elevation alpha, these are the motor filters. This filter is there to smooth the motor rotation. So this will introduce dither to the motor. That is a kind of noise that is being introduced in the PWM signal. There is no PID control, but for smoothness they have used this dither. So this is a process. Various rotating motors are being used via this dither method to smooth their rotation. So we have to put a minimum value. So let's start from this 0.5 that will smoothen. If your system gets oscillated much frequently, then you need to figure out to increase or decrease. So if you increase this value, this will introduce more noise and more smoother response. That sometimes might can introduce some extra oscillations that might get the whole system unstable. So you have to tinker with that value. So for fair amount, let's just start from 0.5, I think. And there is the ISMA alpha. This is the sensor filter value. So in when you are calibrating the sensor, put this value as low as possible, because that will decrease the slow response time, as it has been mentioned here. It will help better calibrate. But if you increase this value, then it will reduce the noise that is being introduced in the sensor. So it will take much less sensor data, and it will the response time would be much faster, but it will clear much more noise from the sensor. So you have to tinker with that value. So these five factors that are there to make the motor stable. So in your system, first go over and encounter every weight possible and every mechanical parameters as stable as possible, and then come here and tinker with this value and get the minimum oscillation of your system. So if I run the demo program, you can see the rotator in action. I will show you now. It's much smoother, and it will slowly rotate. There you can see. Now the rotator response is much slower. As you have seen in previous videos, the rotor gets much more rapid response, but I have decreased. Those are for prototype. This is for real life, and you can tinker with this value, and you can get much smoother response. The larger the antenna, the more higher risk you are getting your rotator into. That might tear some gears because this is some serious weight. That is around 4 kg of weight, you can see from the axial. If you hold, if you cut the axle and put one of the weight on your hand, this will probably around 3.5, 4 kg around of weight right there, hanging right there. So quite a bit of torque there. So much powerful the torque of the geared motor, the better. So this program is actually better for more linear control systems. So because you can just run this with worm gear arrangement, and much slower and high torque can be achieved, but the accuracy of the system cannot be done less than 5 degrees. So there are errors, but you can, if you calibrate your sensor properly, then it can be close to 5 or 4%. In my case, I have done a decent job. In my case, the error lies around 2 to 3 degrees. I will show you the error. If I run the m command for monitor, and you can see the error for azimuth and elevation. So error is a big deal, so you have to tune your system, and better calibration is required. So that's it for this video, and I will see you guys in the next video.